Next, let us take a look at some properties of integrals. The first property says that the integral of f of x dx between a and a, so an integral where the upper boundary and the lower boundary are the same, is equal to 0. These properties are very easy to verify. You just take the formula, so the integral between a and a, f of x dx, is the antiderivative in the upper boundary minus the antiderivative in the lower boundary, and so we get f of a minus f of a, which is 0. The second property, if I have an integral f of x dx between the boundaries a and b, this is the same as minus the integral of f of x dx between the boundaries b and a. So if I change the order of the boundary, so my upper boundary becomes my lower boundary and vice versa, then the sign changes, so I get minus the integral with the boundaries switched. Also here, easy to verify using the formula ab f of x dx. This is equal to f of b minus f of a. Then we can also write this as minus f of a minus f of b between brackets. And so this is minus the integral of f of x dx. We always first have the upper integral, so here we have a, and then the minus the lower integral gives me b here. So again, the formula can easily be verified just using the formula, the formulation of how to calculate a definite integral. Third property is about linearity. So if I have the integral between a and b of some constant a times f of x plus a constant b times g of x dx, then this is just a times the integral between a and b f of x dx plus b times the integral between a and b g of x dx. So here, if we have a multiplication with a constant, we can take the constant out of the integral, and also the integral of a sum is equal to the sum of the integrals. You can again verify this using the formulation. And then the fourth property tells me that if I have an integral of f of x dx between a and b, and then I add the integral between b and c of the same function, this is just the integral between a and c f of x dx. So the left hand side, if we apply the formula, this is f of b minus f of a, plus for the second part it's f of c minus f of b. So we see that f of b cancels out, and we have f of c minus f of a, or it is the integral of f of x dx between a and c. So what it tells us is that we have 2 times an integral of the same function. So here we have 2 times the function f of x, and we have that the upper integral for the first is equal to the lower integral of the second. Then we can put those integrals together and just calculate the integral between a and c of the function f of x dx. So we just take here the lower boundary and we go to the upper boundary of the second integral, because the middle part, the b, is the same for both integrals. Can we also explain these properties intuitively? Yes, we can. For that, what we need to know is that integrals correspond to areas. So this can be shown. It can be shown that an integral corresponds to an area. We will not show this, but in particular it means the following. Suppose that we have a function f of x which is completely positive on the interval ab. If we then make a plot, make a sketch of such a function, we get the following. So we have a function y equal to f of x. This function is completely positive between a and b, and then we can show that the area below the curve, so the area below the function f of x and between a and b, that this area a is equal to the integral. So the integral f of x dx between a and b is equal to the area a. So it is the area between the curve and the x-axis. If you write it out, it is the area bounded by x equal to a, x equal to b, y equal to 0, so this is the x-axis, and then y equal to f of x, which is the curve. So these four functions, they define the boundaries of the area A. If f of x is a negative function, so f of x is smaller than 0 on the interval ab, then we have the following plot. Here again we can define the area A being the area between the x-axis, the curve a and b. But if we relate this area to the integral, we get that the integral of f of x between a and b, this integral is minus the area a. Why is this the case? Because an area is always positive. So a is an area, is positive, but the integral, if you want to calculate it, you will see that this is an integral of a negative function, so this will be a negative number. And so clearly, the integral will have to be the negative value of the area. If we then have a function which looks like this, you see that there is a positive part and a negative part. And so what we will do is we will split this integral as a part where the area is negative and a part where the area is positive. So we get an area A1 for the negative part and an area A2 for the positive part. In this case, the integral between a and b f of x dx, this is equal to the area A2 minus the area A1. Why is this? Let's call this middle point C. We can then use the calculation rule. So the integral between a and b f of x dx is the integral from a to c f of x dx plus the integral from c to b f of x dx. Then the first part, the integral is negative, the area A1 is positive, so this is minus A1 plus the area for the second part, which is positive A2. So we have this integral is A2 minus A1. So it is the positive area, so the area which is on the positive side of the x-axis, minus the area which is on the negative side of the x-axis. If you have a function with multiple crossings of the x-axis, you can do the same thing. So by extension, the integral of f of x dx, so the integral between a and b f of x dx, in this case is minus a1 plus a2 minus a3 plus a4. If we then want to relate the properties to the areas, we could say the following. So for the first property, what it tells me is that the area below a single point is 0, which is trivial. If you have only a single point, there is no area under this point. And the fourth property, for example, just tells me that the total area is the sum of the different areas. So it's what we did in the previous part, where we added the green and the yellow areas together to get the total area. Let's then make an example on the link between areas and integrals. So for example, calculate or find the area of the region which is lying above the x-axis and below the curve y equal to 3x minus x squared. To find this area, we have to solve a definite integral. And to solve this definite integral, we also need the limits of integration. So first what we have to do is we have to determine the points of intersection. So where are these two curves intersecting each other? So we have two curves. On the one hand, the x-axis, y equal to 0. On the other hand, y is 3x minus x squared. When is there an intersection? When these two are equal. So when 3x minus x squared is equal to 0, or we can rewrite this. This is 3 minus x times x is equal to 0. So it means x is 0 or x is equal to 3. And then in the second step, we have to calculate the area. So we have to calculate the integral of f of x between the limits of integration. So we get the integral f of x dx between 0 and 3. So when we sketch this, we get a function like this. So we have a function going from 0 to 3 here. And we see that the function is completely positive. So this one is y equal to f of x. This is the curve. And then we have to find the area below this curve, but above the x-axis. So the area is equal to the integral. It is already on the positive side, so we don't have to change the sign. So the area A is the integral between 0 and 3 of f of x, so of 3x minus x squared dx. We calculate this integral, so this is 3x squared divided by 2 minus x to the power 3 divided by 3 between the boundaries of integration, so between 0 and 3. This is 3 times 9 divided by 2 minus 27 divided by 3. And then the same thing in the lower boundary, but this is just 0 minus 0. So it is 27 over 2 minus 27 over 3. And if you calculate this, you get 9 divided by 2. So the area we are looking for is 4.5. For the fifth property, assume that f is odd. So if f is an odd function, then the integral of f of x dx between the boundaries minus a and a is just equal to 0. So f odd, this means that f of minus x is equal to minus f of x. And it's also important to note that the lower boundary here is minus the upper boundary. The easiest way to see this property is just by making a sketch. Let's assume that we have such an odd function between the boundaries minus a and a. This function then defines two areas. The area A1 on the left side, which is below the x-axis, and the area A2 on the right side, which is above the x-axis. We can then write the integral, so the integral minus a to a f of x dx. This is equal to minus a1 plus a2, but since f is an odd function, the area A1 is equal to the area A2. So because f is odd, the function on the left part, so the function left of the y-axis, is just the mirror image across the origin of the function on the right side. And so the areas that are defined are exactly the same. The only difference is one time the area is below the x-axis, the other time the area is above the x-axis. And so if we apply our formula for a definite integral, it is the positive area minus the area which is on the negative side, but a1 is equal to a2. So the integral, the total integral, is equal to 0. Then there is a similar property for even functions. So if f is an even function, then the integral between minus a and a f of x dx is just 2 times the integral of f of x dx between 0 and a. So if we look from minus a to a and we calculate the integral, then this is just the same as the integral from 0 to a, but times 2. The fact that f is an even function means that f of minus x is equal to f of x, and if we make a plot, if we make a sketch again, we get something as the following. So we see that for an even function, we get a mirror image across the y-axis. So the function left of the y-axis is equal to the mirror image of the function on the right side of the y-axis. And so the areas which are below the curves will also be identically the same. Both of the areas are on the positive side, and so we can write this integral, the integral from minus a to a f of x dx. We can write this as the integral from minus a to 0 f of x dx plus the integral from 0 to a f of x dx, which is equal to a1 plus a2, but a1 and a2 are the same, so this is equal to 2 times a2, or 2 times the integral from 0 to a f of x dx. And then the seventh property. For the seventh property, we have the integral from 0 to a f of x dx. This is equal to the integral from 0 to a f of a minus x dx. To prove this property, we will apply substitution. So substitution will also come back later where we look at it more in detail. But basically what we will do is we will substitute my variable x through another variable. So we have on the left hand side a variable x which goes from 0 to a. And I will replace it with another variable t. So set t equal to a minus x in this case, because we want to go to a minus x on the right hand side. If x is equal to 0, this means that t is equal to a minus 0, so it's equal to a. If x is equal to a, then t is a minus a, this is 0. So if I change to t, then my new boundaries, my new limits of integration go from a to 0. Furthermore, I have to see what happens with my differential. So t is a minus x. This also means that x is a minus t. And so dx, this is just the differential of x. This is the differential of a minus t. But in this, t is the variable and a is just a constant. So this is minus dt. So when we start from the left-hand side was the integral from 0 to a f of x dx. We then want to replace everything. We want to rewrite everything in function of t. So my integral becomes the following. My lower boundary x equal to 0 becomes a lower boundary t equal to a. My upper boundary x equal to a becomes an upper boundary t equal to 0. F of x, so x was a minus t, becomes f of a minus t. And then dx is minus dt. We rewrite this. This becomes minus the integral from a to 0, f of a minus t dt. And then we know that if we change the limits of integration, so if the upper one becomes the lower one becomes the upper one. So we write the integral from 0 to a. Then we also change the sign. So it is minus. Together with the other minus, it becomes a plus. F a minus t dt, which is the right hand side, which we needed to prove. And we can also extend this property. So if we have an integral from a to b, so not from 0 to a, but from a to b, so we have a lower boundary and an upper boundary, which are both different from 0, f of x dx. This is the integral from a to b, f of a plus b minus x dx. If you take a closer look at this, you see that the previous case is a special case of this one. So if a would be 0, my lower boundary is 0. This is just the integral of 0 to b f of x dx equal to the integral from 0 to b f of b minus x dx, which is the property that was shown on the previous slide. For the proof, we do the same thing, so we also do a substitution, but now we set the substitution t is equal to a plus b minus x, because this is what we have to work to, this is what we have in the right hand side. So with this substitution we can look at the limits of integration. If x is equal to a, then t is equal to b. If x is equal to b, then t is equal to a. We also know that x is equal to a plus b minus t, and so d of x is d of a plus b minus t, so it's minus dt, because a and b are just constants. And then we have the left hand side. The left hand side was the integral from a to b f of x dx. We apply the substitution, so we apply our change. A, so x equal to a is the same as t equal to b. X equal to b is the same as t equal to a. F of x, so x becomes a plus b minus t, and d of x is minus dt. So this is minus the integral b to a f of a plus b minus t dt. We then change again the order of the limits of integration, so we also change the sign. This is the integral from a to b f of a plus b minus t dt. And then since t is just a variable, it's just a variable of integration, we can change it. It's just a letter. It doesn't matter which letter we use. And so we have here the right hand side, and this completes the proof. For everything that we have done so far, we made one implicit assumption. So remark, we implicitly assumed that my function f was continuous. So basically everything that we saw before was under the assumption that f was a continuous function over the interval ab, so between the limits of integration. So actually what we would have had to say, so what was the correct way of defining a definite integral, would be that if f is continuous on the interval ab, then the integral between a and b f of x dx is the antiderivative in b minus an antiderivative in a. So this for any antiderivative, so for any f, capital F, such that f prime, capital F prime, is equal to small f. So f, capital F, must be an antiderivative of f. And then we also have the remark we made before, that g of x, which is the integral from a to x f of t dt. So this is a function of x, so x is still a variable in this case. This function g of x is continuously differentiable. So it means that the derivative is also continuous, and g prime of x, so if we take the derivative of g, we get the function f of x. Then what if f is not everywhere continuous? So f will anyway be a piecewise continuous function, so it means that f is continuous on different parts, so piecewise continuous, meaning that the function f is continuous on certain intervals. So it's continuous on sub-intervals, and what we then do is we just split the integral over the different intervals. So we split it over the different continuous parts. Take, for example, the following function. We see that the function f of x actually consists out of three parts: a subfunction f1, a subfunction f2, and a subfunction f3. Let's say that the subfunction f1 goes from a to c, f2 from c to d, and then f3 from d to b. Then the integral of f of x dx from a to b is just the sum of all the sub-integrals. So it's the integral from a to c for the first continuous part, so f1 of x dx, plus the second part, which is the integral from c to d f2 of x dx, plus the third part from d to b f3 of x dx. To conclude this class, let's look at some examples of integrals. So the goal is that you first try these yourself before looking at the solutions. So the examples are, first of all, the integral of 10x to the power 4 minus 2 times secant squared of x dx. The second one, the integral of 2t squared minus t squared root of t minus 1 over t squared dt. For the third one, calculate the integral of x squared over 1 plus x squared dx. Fourth one, find the area under sine of x and then between values 0 and pi. Next, if f of x is the integral from x to 3 e to the power minus t squared dt, find then the derivative of f of x. Then suppose we have g of x, which is x squared times the integral from minus 4 up to 5x of e to the minus t squared dt. Find the derivative of g, so find g prime of x. And then the last one, find d dx of the integral 1 to x to the power of 4 of the secant of t dt. For the first one, we just apply linearity. So this is 10 times the integral of x to the power of 4 dx minus 2 times the integral of secant squared of x dx. This is 10 times x to the power of 5 divided by 5 minus 2 times the tangent of x plus, of course, a constant. Don't forget the constant, it's very important to include it. So this is 2 times x to the power of 5 minus 2 times tangent of x plus a constant. Here, what we can do for the second one, the easiest thing is first make the fraction. So this is the integral of 2 minus the root of 2 minus 1 divided by t squared dt. So it is 2 times the integral of dt minus the integral of root of t dt minus the integral of t to the power minus 2 dt, which is 2 times t. The root of t is t to the power 1/2, so it is t to the power 3 over 2 divided by 3 over 2. And then for the final term, this is minus t to the power minus 1 divided by minus 1 plus your constant. So it is 2t minus 2 over 3 t to the power 3 over 2 plus t to the power minus 1 plus a constant. How can you easily solve the third one? Well, actually it's quite simple. You want to find something that you know, so a derivative that you know. You don't know x squared over 1 plus x squared, but you do know 1 divided by 1 plus x squared. So what you will be doing is here, this is also x squared plus 1 minus 1 divided by 1 plus x squared dx. And then you just split it. You take the first part, so x squared plus 1 over 1 plus x squared is just 1 times dx. And then you have minus 1 divided by 1 plus x squared dx. The first one is easy, this is just x. The second one you know is the inverse tangent, so this is tan minus 1 of x plus your constant. So here the trick is just to rewrite your expression in such a way that you can split it into different parts which you can calculate very easily. Exercise 4, what you have to do is you have to rewrite this area as an integral. So the area is the integral of sine x between 0 and pi. If we make a quick sketch, we see that sine of x is completely positive between 0 and pi. And so we don't have to make any modifications. The area is just the integral from 0 to pi sine of x. This is minus cosine of x between 0 and pi. And so it is minus of minus 1, or the area is equal to 2. If you have to calculate an area, always be sure to check that in the end the area is a positive number. If not, then you probably have made an error with the signs and you have to add a minus sign somewhere in your calculations. For the fifth one, we will be applying the property that g of x is the integral of a to x f of t dt. Then g prime of x is just f of x. So here f of x is an integral from x to 3 e to the minus t squared dt. What we want is that x is the upper boundary, so we have to change them, and also the sign change. So this is minus the integral of 3 to x e to the minus t squared dt. This is my function f of t. And so if we look at the derivative of capital F, so f prime, which is now the g prime in the red formula, this is just f of x. So this is e to the minus x squared. For the sixth one, we have a combination. So we have x squared times an integral. And so what we do is apply the chain rule for the derivative. So the chain rule, this tells me that I have to take the derivative of the first part times the second part, plus this first part times the derivative of the second part. So I get here 2x times my integral plus x squared times the derivative of my integral. We now have one additional problem. So here, this upper boundary, this is 5x instead of x. So we know what would happen if this is x, but we don't have x, we have 5x. So we have to modify the formula a bit. Instead of g of x, we now have g of u of x. So we have a function of x as the upper boundary. So this is the integral from minus 4 to u of x, f of t dt. If we then want to find the derivative, we have to, again to use the chain rule. So the derivative of gu of x, so d dx, so the derivative 2x of gux. This is the derivative to u, so du gu times the derivative to x of u of x. So we have to derive g to u times the derivative of u to x. Let us retake the final formula that we had. So this was equal to 2x, the integral minus 4 up to 5x, times e minus t squared dt, plus x squared times, and then the integral minus 4 to 5x, e minus t squared dt derived. This is equal to 2x times this integral, so it doesn't change anymore, this part, plus x squared times the derivative of the integral. Let's write this now in the form as we saw on the previous slide. So say g of u of x is the integral of minus 4 to u of x, e to the power minus t squared dt, and then we know that u of x is equal to 5x. This part here is my f of t, and so if I derive g of u to u, I know this is f of u, so my derivative here is f of u of x times the derivative of u of x to x because of the chain rule. So finally we get this is 2x times the same integral again, plus x squared, f of u of x, so this is e to the power minus t squared, so minus u x squared, u of x is 5x squared, and then we have to derive 5x to x, so this is 5. Or we get this plus x squared e to the power minus 25x squared times 5. And then for the last one, it's a similar problem. Here we have an upper bound of x to the power 4 instead of x. So again, we have to use the chain rule. In this case, g of u of x is the integral of 1 to u of x secant t dt, and u of x is x to the power 4. So if we derive this, so d dx of g ux, this is the derivative of g to u, so d du g of u times d dx u of x. This is the chain rule that we apply. Then the first part is a derivative of g of u, so it is my function f of t, which is in this case secant of t, so it's a secant, but within u of x, so secant of u of x times the derivative of x to the power 4. Here we know that u of x is x to the power 4, so this is the secant of x to the power 4 times 4x to the power 3. So the final answer will be 4 times x to the power 3 times the secant of x to the power 4.